Now. So welcome everybody to our last summer session on our AGN seminar series. So thank you all for joining, and thank you so much, Erin, for agreeing to give our final talk. We've been very excited to hear your work. And so Erin got her PhD from UCLA, working with Matt Malkin, who's here too. And she then went on to do a postdoc position at MPE in Germany. And she got then an NSF postdoctoral fellowship, which she conducted at University of Washington. And she then joined the faculty in the Department of Physics and Astronomy at the University of Alaska, Anchorage, where she is currently an associate professor. And Erin is really at the cutting edge of the field in integral field spectroscopy with adaptive optics, particularly in the near infrared. And she's involved in numerous impressive number of cutting edge multi-wavelength collaborations, including, and I learned this only recently, I was like, oh my God, you're doing so many different things. She's on the Gatos collaboration, which involves ALMA and JWST observations with additional data from numerous other facilities, including Sophia. So I was like, oh my God, wow, that's a lot of different data sets to work with. And she's also on the LAMA collaboration, which involves VLT Symphony data, ALMA data, and HST data, in addition to additional data sets from APEX, JCMT, VLT Extruder. And of course, she's played such an integral role in the KONA collaboration, which you've heard about before with Francisco. I think he's here as well, which is Keck Osiris data of nearby AGN. So as you can see, she's just spanned numerous cutting edge multi-wavelength collaborations with all these really cutting edge facilities. She's been investigator on numerous proposals with data from premium ground and space-based facilities, including most recently JWST. So we're really excited to hear about that. And she's also had impressive grant funding from NSF and NASA and numerous other organizations. She's also, on top of all of this, I was impressed, she's the director of the University of Alaska Planetarium and Visualization Theater. And she's also done a lot of work in diversity and inclusion. In fact, she won an award for her work in that arena. And I was really happy to see that she's leading programs supporting undergraduate research. So she's mentored over 30 undergraduates, and I was like, oh my God, that's a lot of work, and that's impressive and really critical work. And she's also involved in programs that provide research opportunities for traditionally underrepresented undergraduates in the natural sciences, where they work with faculty mentors. And I saw that, she's been an amazing mentor, and she's received awards for teaching that date back all the way to when she was a graduate student. So I can see that teaching and mentoring has been really an important role, and whoever is being mentored by her, you're very lucky. And she also got the UAA Chancellor's Award for Excellence in Diversity. So, it's really impressive, all of the scientific expertise that Erin has been doing. And on top of all of that, her dedication to teaching, mentoring, and diversity is really commendable. And I should say that I have thoroughly enjoyed numerous conversations with Erin over the past year and this crazy pandemic year. And I remember riding the Beltway and we were discussing, I was picking her brain about all you can do with really high spatial resolution observations using a laser beacon where you can do adaptive optics in the visible. And as I was driving in the Beltway, that was when the craziness was happening on at the Capitol. And I remember that my phone got a sudden alert, and we were having this really idealistic conversation. And I remember we were both sitting there, and it was a very surreal moment. And I can tell you that over the past year in these AGN discussions, it's been, just really nice, sharing discussions with this inspiring group of scientists, and these seminar series really have been an inspiration, and listening to you all has really been a gift. So with that, I wanted to introduce Erin to you, and she is going to be talking about outflows and what these high spatial resolution multi-wavelength observations have taught us. So Erin, I'll let you take over.
Great, thank you. Let's get my screen. I'll just first start with saying thank you to Shavita and Gabby for organizing this series. As has been said, this has been a great break from the chaos that has ensued over the last year and a half of our lives. So thank you for organizing this and for inviting me to give a talk. So I'll also really thank all of the previous presenters, because it has made what I'm going to present a lot easier, because I found myself thinking, oh, well, there was this presentation earlier this summer that, that I can refer to. So there's a lot of what I'll present here that ties back in with what we've already talked about this summer. And there's been a lot of great presentations. So thanks to the previous presenters for a great summer of discussions in science. So yes, I'm going to talk about feeding and feedback and AGN and the cycle that we now think is happening on the scales at the very central kiloparsec or so. And I'll just start off by kind of motivating this, as everybody has done thus far, and so I won't spend too much time on this. But of course, we have this idea that the host galaxy and black hole are co-evolving, motivated by the fact that we see these empirical correlations between the mass of the black hole and various host galaxy properties. You can see an example here with the dispersion, which you can take to be bulge mass approximately, and the fact that these two properties, the black hole mass and other properties of the host galaxy, are correlated, tells us there's some connection between the two, and we have ideas of what that might be. The two key processes being feedback from the AGN, as well as maybe the feeding of the black hole, the processes that bring the material from the host galaxy down to the black hole that enable that growth of the black hole in the AGN process. But the details of the physics is not there at an understanding yet where we really can say this is what explains the coevolution of these two components of the host galaxy components and the black hole mass. And a lot of what's been proposed to explain this is galaxy mergers. And we saw the beautiful results that Vivian shared, I think it was last week, where you can have a host, two galaxies, gas-rich disk galaxies, for example, merge. There's loss of angular momentum, and a bunch of stuff's going to dump down to the center, and then in time you form one new galaxy. And in the process of doing so, there are various phases in which the black hole will end up growing. It'll go through an AGN phase. But do these major mergers explain everything? And it turns out really that is not the case, especially at Seyfert AGN, Seyfert luminosities. The AGN are preferentially in undisturbed morphologies if we look at the host galaxy. And so what's shown in this study here, and there are many others that have had similar results, where the AGN and the control here is an otherwise similar galaxy, but the black hole is not actively growing at the time of observations looking at that host galaxy. So that the inactive and active galaxies that have been matched by various properties, what we see is the fraction of AGN that sit in undisturbed galaxies is comparable to the inactive galaxies. So there's nothing that is the smoking gun saying that, oh, well, the AGN, they all sit in active galaxies. And so this process is related to a major merging. We know that a major merger, part of that process is likely black hole growth, and an AGN will be observed, but we have a lot of AGN activity happening in undisturbed galaxies as well. In fact, most of the Seyfert-like AGN are in undisturbed galaxies with no suggestion of a major merger. And it's also the case that 50% of AGN reside in disk galaxies, where there's no evidence of even past major merging. It doesn't, not even an active disturbed scenario, but they're in a disk galaxy where it looks like it's been stable for quite some time. And so it doesn't look like that major merging is going to be the dominant fueling mechanism for that black hole growth. And even in cases where there is a major merger, simulations are now suggesting, for example, the work done by Phil Hopkins, that even in these major merger processes, it comes down to disk processes that carry the material down to the black hole. So even though there might be loss of angular momentum to get it close, there's still a dependence on these disk processes to carry the material from kiloparsec scales down to, let's say, hundreds or 10 parsec scales. And then there's, of course, getting even further in. But in that circumnuclear region, the central kiloparsec, the disk processes are what dominate that fueling process, even in the crazy environment of a major merger occurring. So understanding fueling of AGN and the feeding of that black hole, it really comes down to understanding the disk processes that are occurring in these galaxies. And another important point is the time scale, and this has been brought up in a few other talks, where it looks like that the AGN duty cycle is more in the range of 10 to 100 million years, with a flickering on and off of much shorter than that. So what are the relevant physical scales that we should be expecting to see differences in if we take a sample of AGN and inactive galaxies, are looking at the host galaxy in general on very large scales? Would we even anticipate that the current state of that galaxy should reflect something that's relevant to the active growth of the black hole and an AGN phase? And really, there's no reason one should, just because there's angular momentum loss out at several hundreds of kiloparsecs, it doesn't mean that that's relevant to what's happening down all the way at the black hole. And so simulations show that it's expected that this AGN duty cycle is pretty short. And so considering the dynamical time scales, let's say at 100 parsecs, they're going to be about 2 to 3 million years. So this would be more comparable to what we would to the expected AGN duty cycle. And so just what we've been able to measure of motions of molecular gas in nearby AGN would tell us that the relevant physical scales to be looking at, where we might anticipate that there would be a state of that material on those scales relevant to the current state of the AGN, would be somewhere around 100 parsecs. And potentially even less if timescales were shorter. The on-off cycle of AGN was even shorter. So the relevant scales here, if we need to get down to 100 parsecs, as I'll get to, it's really nearby AGN that it's relevant. We're only able to resolve those scales in nearby AGN. If we get too far away, then we're just not able to resolve the physical scales relevant to the current state of the black hole growth. Now getting to smaller scales, this is the classic AGN torus model. And this is where, what was proposed as an explanation for the different type of AGN that we see, Seyfert 1, Seyfert 2, Seyfert 2 being those that we can't, the central region is obscured because we're looking through some sort of obscuring material. It's known as the torus. And of course, this simple picture was never really thought to be here, this is the solution. And it was, holes were poked in the torus, and there are all these iterations of what can we do to actually make this match the observations. And so there are these various iterations on what that torus should look like. And then getting down to, what observations do we have to constrain these models? Relatively recently, observations have suggested that perhaps it's a little more complex than we even originally believed, knowing that, okay, it's not as simple as this donut-like structure, but perhaps there's more of an in and out cycle of material, that torus is not static. And pushing us in that direction were several pieces of evidence, but one really big piece that came was the discovery of, in the mid-infrared, looking at the dust emission, that there was polar. And so if we're talking about dust, you'd anticipate, looking back at our classic picture, the dust should sit in this obscuring structure here. This is where the dust is needed there, because that's what's going to obscure our view of the central region. And so the fact that there was a torus-like structure in the mid-infrared data, so we're looking at very small scales. In the color here is where water masers were found in Circinus, and then we see in white are these torus-like structure, but we also see an extended component is shown here in the green. And so this polar dust structure came as a surprise. And then there was following up on that, as was found in 2019 paper, doing a survey of a larger sample here. This is the extended emission that's shown. And what we see is that in green is the axis of outflows, so perpendicular to what we would have thought would be where the torus would be. And you see there's significant extended emission in the mid-infrared along the outflow axis. And so this did not fit our picture of what the torus, where the dust would be on those smaller scales. And we do see direct evidence of, dense gas seen with ALMA on 10 parsec scales. There's a rotating component that was seen in a few galaxies and now many more, in which we do see something resembling a torus, and that there's a lot of cold gas traced with CO, and it's on scales that one would say is consistent perhaps with a torus, but it's not in the static state might one had anticipated it would be. It's very turbulent and homogeneous disk-like structure. And here's in NGC 1068, and we saw some of these results in a previous talk, where this is tracing quite dense gas. This is HCN, and we still see a pretty turbulent structure. It's rotating gas, but it's not as calm as we might anticipate. And in fact, as I'll show later on, there's quite a bit of evidence now that we see in the CO that there's evidence of outflow as well. So this brings us to kind of this new paradigm of what we think of as a torus, what that central obscuring structure might look like. And it looks like it's some sort of dynamical structure where it's a cycle of material in and material coming out. And so I really like this this model here. This is this cycle will be driven in this model, a radiation driven, what's termed as the fountain model, where you have material coming in, and then the winds, the feedback from the AGN ends up in these winds, and not all of it is going completely out of the region, but some of it will cycle back through, and you have kind of this failed wind. So this turbulent region here, where you see the molecular gas, cold and cold dust, in this turbulent region where you have this failed wind. Some of it may make it out, and where the boundaries are between what the state of that wind would be and how that relates to the AGN properties will really help us build this picture of what this cycle may look like. Out at hundreds of parsecs, you can see the cold molecular gas. There's also, of course, warmer gas in there as well that we can trace in the near infrared. And then I won't talk about it much today, but there's a whole question of what kind of star formation is occurring on these scales as well. And so this new picture of the cycle of this dynamic torus, we have material coming in to feed the black hole in the central region, but that feedback results in winds coming outward that then cycle in, and you have this material, potentially some fraction of it potentially falling back in. And so you end up with a quite turbulent disk. And there are models that have been put forward by Sebastian Honig and his students. This is one from Williamson, in which testing various wind parameters and configuration of the density of the material in the surrounding region. And we can predict what would this kind of radiation-driven fountain model look like on scales from 1 to 100 parsecs. And in these models, we see a variety of things. There's the CO gas that we can trace with ALMA. There's the near infrared gas that we trace. And there are some large studies now that I'll share that are tracing this molecular gas. And then there's H2 lines that we'll be able to observe, for example, with JWST for the first time and really get the kinematics of what the molecular gas is doing at those wavelengths and temperatures. And so there's a variety of predictions of the configuration there on hundreds of parsec scales. This wind would look potentially like this if we have one configuration on wind speeds and what the density of the surrounding material is. And then we can also end up with something very different if the situation at density of material primarily is changed, but also that wind speed, the launch speed of the material from the very central region. And you can see in the very central region here, so this is central 10 parsecs or so, there's some interesting structure that if we can get down to these scales, it would be great to be able to get the constrain the outflow and the structure properties using these observations. And so what we have is to try to understand and build a picture of what things look like in the central region of these AGN, whether it be the process of a major merger, or whether it's a Seyfert galaxy sitting in an isolated disk. We really are dependent upon those galaxies that are nearby to us to be able to study things in enough detail to constrain these kinds of models. And so what we aim to do with the surveys that I'll talk about is to quantify the physical processes that we see happening. And what we know is if we just look at a handful of galaxies, we're going to get a different story with each one. And really, it is true, each galaxy has its own story to tell, but we need to be able to build up the statistics to be able to get a meaningful conclusion of AGN more widely, at least Seyfert luminosity AGN. And so identifying the inflows and outflows and what is driving those processes will hopefully provide that insight we need to start building the story of how the black hole mass connects with the host galaxy. So I'm just going to share some results from a few of the surveys. These are the surveys that Savita had mentioned I'm involved in. And the first is the Kona sample. I'm not going to go through a lot of things have been discussed already. Francisco did a great job introducing the Kona sample and talking about the outflows. And this is a sample that's nearby galaxies, what's shown in the background here. These are the K-band continuum. We have approximately half Seyfert 1s, half Seyfert 2s, and we get down to spatial resolutions of about 38 parsecs, considering the point spread function. So most of these are adaptive optics assisted observations. I'm just comparing our sample to the BAT sample. So this is a hard X-ray, thought of as an unbiased sample of AGN. In the blue and green is shown the BAT AGN, and then in red are the Kona galaxies. We also have a collection of galaxies in the Kona sample for which there was no BAT detection. And so these are higher column density galaxies where there's more obscuration. And so that'll be an interesting addition to our sample to see how those galaxies may differ in any properties. There's also the LAMA sample, so the local luminous AGN with matched analog sample. And whereas the Kona galaxy has 40 galaxies that are all Seyfert, the Llama sample has 20 Seyfert galaxies and 20 inactive galaxies that are matched based on those host galaxy properties. So this is driving more the question of what do we see is different in local AGN in these Seyfert galaxies compared to those that otherwise, based on the host galaxy, look to be similar or identical based on morphology, inclination, for example, the stellar mass, which we use the H-band luminosity as a proxy for. But how do they look, for the inactive galaxies? That black hole is not growing. And so hopefully we're getting down to the scales where it's relevant to what the black hole growth state is. And so looking at the inactive galaxies and comparing those to the Seyfert galaxies, we can identify what is unique about those AGN. And so again, this is compared to the BAT sample. This is a volume limited sample selected here. And then a subset of these are what I will present results for. And you can see the X-ray luminosities for the AGN and the inactive galaxies shown in blue here that have been selected. And for both of these samples, it's near infrared IFU data that I'll be sharing. And this is just an integrated spectrum here of this really nice galaxy. Obviously, all of the galaxies don't have such spectacular spectra, but this is Mercurian 1066. All of the galaxies that we've studied, except for just a handful where the signal to noise is too low, we have the molecular hydrogen emission line here at 2.12 microns. So that's tracing the warm molecular gas. There's also ionized gas that we can trace with bracket gamma, as well as the silicon-6 line in the majority of these galaxies in both samples are both the Llama and the Kona surveys. There's also these CO band heads, which are really important because these allow us to trace the stars. And so we can trace the kinematics of the stars. We can get a handle on what the kinematics, what the kinematics of the gas, what the stars are, which tells us what the gravitational potential is, which we can then use to infer what's the rotation of molecular gas, for example, and what components of those dynamics are attributed to inflows and outflows rather than a rotation. So the stars are used to help constrain what we can anticipate of the rotation due to the gravitational potential. And so these are just some maps here, Mercurian 1066. This is IFU data. So we get to map out the motions, the distribution of the stars and the molecular gas, the ionized gas. And so there's a lot of great structure in these galaxies to be studied in detail. I'll just start off with saying we knew from a kind of a pilot sample that looking at non-AGN and AGN, that the surface brightness of the molecular hydrogen was enhanced for the AGN compared to the non-AGN. In fact, these are upper limits here. And so for 3 of the 5 non-AGN in this pilot sample, we didn't even have detectable molecular hydrogen within the central 100 parsecs, even extending out to 200 parsecs. And then here shown is the total molecular gas and the luminosity in the AGN and the matched quiescent galaxy. So we see on 100 parsec scales that Seyfert galaxies are showing a unique property compared to inactive galaxies, and that they have more molecular gas emission in the central region, which one could infer to mean that there is more gas present in those Seyfert galaxies. This has now been confirmed with the Llama sample. It's a much larger matched sample of galaxies. So there's AGN in red and then inactive galaxies in blue. And you can see again that the AGN have higher surface brightness of molecular hydrogen. So again, confirming that warm molecular gas is more abundant in AGN on these scales compared to the inactive galaxies. And the Kona sample breaks this down into Seyfert 1s and Seyfert 2s. And we don't actually see any statistical difference. Shown in the back are the individual galaxies, the dashed lines, those with upper limits. And then in the solid lines here are the subsamples, the median for the Seyfert 1 and Seyfert 2 subsamples. And we statistically there's no difference. There's quite a spread in the H2 surface brightnesses, but statistically there's not a significant difference between those two subpopulations. I'll mention that Dan Delaney, my grad student, is working on a much larger sample of Seyfert galaxies. We're compiling a large atlas of all local AGN that have been observed with the near infrared IFU data. And it looks like potentially with a larger sample, you can break things down to Seyfert 1, Seyfert 1.2, Seyfert 1.5, and the different subcategories that we have for our Seyfert class or AGN classifications. And maybe we're getting a hint there of some separation of the Seyfert types. So it'll be interesting to see where that research leads. So I'll just show you here some maps of the molecular hydrogen. So you can see the OSIRIS rectangular field of view, and some of these we got two different position angles of the instrument, and so you can see we've mapped out what this looks like. You can see in general the molecular hydrogen has nice rotation pattern, and that in the velocity structure we see blue on one side, red on the other, where the red is going away from us. We see that rotational pattern. But if it were just simple rotation, we'd see a nice zero line through the center. But you can see there's a lot of structure. Here's a nice example of NDC 4388. There's a lot of structure there. So we can already just see right away that the molecular hydrogen, while dominated by rotation, has a lot of non-rotational component as well. And just looking at the azimuthal average of the flux distribution, it's centrally concentrated, but you can certainly see there are examples of galaxies where the molecular hydrogen has other structure as well. Again, 4388 in the center, down on the left here. Yes, it's centrally concentrated, but you see knots of emission off to the side. And so there's some structures there that help us disentangle what other processes that are occurring just beyond rotating in gravitational potential. And considering the molecular gas, looking at the velocity dispersion, so again, azimuthal average of velocity dispersion, the dashed lines in the back represent the individual galaxies, and then a median's been taken for the different Seyfert 1, Seyfert 2 types. And you can see the molecular hydrogen is pretty consistent throughout that central region of what we see in these galaxies, all the way out to 250 parsecs. We see that dispersion is pretty flat, and it's pretty low compared to what we see the same scales of those stars. So the stars are representing the bulge. We're looking through the bulge. We have a bulge component there, so the dispersion is a little bit higher. If there was a strong disk component of a supernuclear star population sitting there, then that could be bright enough to then dominate the kinematics, and we would see a downturn in that dispersion to then be potentially more consistent with what we see in the gas. And we don't see that as a general property, though, in some individual galaxies. We definitely see an extra component to stars in that center, and that population influences the dispersion that's measured more significantly. But in general, Seyfert galaxies seem to have a pretty dynamically cool, I wouldn't say cold, but it depends on, temperature is relative here. It's a dominated by rotation, I'll say, molecular hydrogen, that warm molecular hydrogen in Seyfert galaxies. We definitely do see signatures of inflows and outflows, which I'll get to. And just real quickly, looking at the ionized gas, this is silicon-6. We've done this, we have all of these data for bracket gamma as well. Francisco showed some great examples of the modeling that's possible with the outflow here. Just to compare it to what we see in the molecular hydrogen, although the molecular hydrogen was centrally concentrated, we do generally see it throughout the field of view that's measured. It's present out to hundreds of parsecs, whereas with silicon-6, we see it's far more centrally concentrated. And so that as a result, that the half width, half max of that azimuthal average, or of a 2D fit, is a little bit smaller, instead of it being like, was it 40 kilometers or parsecs rather. It's a little bit smaller in the silicon-6, so more centrally concentrated silicon-6. Although there are lots of examples where it's collimated, it's in an outflow structure that's very clear, rather than being just centrally concentrated. So the half width, half max of the flux distribution of the ionized gas in the case of silicon-6 is 26 parsecs, and the dispersion is significantly higher in comparison to the molecular gas. So we see a lot more action with the ionized gas as might be expected. And we see potentially, you know, a trend for Seyfert-1s to have a higher velocity dispersion in silicon-6. Although you can see there's a lot of spread here in the individual galaxies, and you see that reflected in large standard deviation error bars here for the type 1s. And getting to the two-dimensional kinematics here. So I've shown here are the case of NGC 4388. And what's possible with these data, looking at the kinematics, is to constrain what the rotational component is. So here are the stars in this case. And this is the first step. We can symmetrize that velocity field and determine what the major axis is of the rotation. And then we can do this with the stars. We can do this with the gas. The stars we know are just responding to the gravitational potential. And so we help use that to constrain what we can anticipate of the rotation of the gas, and then isolate the inflow and outflow structures of the non-rotational components. But just looking at what's the major axis would be of the rotation through this simple approach of symmetrizing the field, we can compare the position angle of the stars and the gas. We can also take that symmetrized field and simply subtract that from the observed field, and we can get residuals, which are, and with this approach, rather crude estimate of what the, kind of a measure of what the non-circular motions would be. A full kinemetry analysis is underway now, and so that will provide us a more detailed view of what the non-circular motions are. And so that, but just considering what we get of the position angles of the rotational component of the stars and the molecular gas, we can ask the question, well, are the stars on these scales on hundreds of parsecs, is that rotation consistent with what we know of the host galaxy? And it looks like, yes, looking at the photometric position angle and comparing it to the kinematic position angle that we get from the stars, you can see this general consistency here. Those that have kind of an orange highlight around them are those that are known to have resolved K-band continuum. This is driven by resolved stellar component in the central region. So indications that potentially there is an additional stellar component. So stars forming within that cold molecular or colder molecular gas disk in the central region. So an extra stellar component there. But even in these cases, you can see this general agreement between the position angles. Interestingly, in this first effort to quantify the residuals, we see that there is a greater potential for there to be larger residuals in the stellar component after removing that symmetrized field when the X-ray luminosity is higher. So those AGN that are more have a higher X-ray luminosity have a tendency to have larger residuals in that stellar velocity field. And so this might be an indication of AGN feedback. And so certainly pushing this further to do more detailed kinematic studies will help illuminate whether that is a real trend there and its significance. And comparing the molecular gas position angles of the kinematics of that disk, the disk orientation to that of the stars on the same scale, it looks like we have cases where the stellar component is, or the molecular gas component is consistent with the stars, but we also have in about half the sample a misalignment by greater than 40 degrees, which it's outside of most of the error bars here. So we have many cases, particularly several where the stellar component is resolved, that where these two components do not agree. They do not align or are spatially coincident, well, kinematically coincident. So, and looking at the same exercise, looking at the residuals of the molecular gas after subtracting that symmetrized field, there is again a tendency, I would say statistically significant in this case, for those galaxies with higher X-ray luminosities to have greater degree of non-rotational components in their velocity field of the molecular gas. So in the Kona survey, and this is also, I think, in large part coming out of the LLAMA survey as well, we find that the stars, the stellar component that we're measuring on these scales, is aligned pretty well with the host photometric axis. And we find that the molecular hydrogen is dominated by rotation. It's also detected throughout the central kiloparsec in comparison to the ionized gas, which is rather centrally concentrated or collimated and ionized along the ionization axis. And I didn't talk about the masses, but going through that exercise and determining what the masses are from the luminosity that we see, we see masses of, gas masses of 10 to 1,000 times more than is required to feed the AGN over a life cycle of 10 to 7 years. So we see a lot of material coming in, more than is needed. Of course, we have the outflows that Francisco presented on top of this. So we have some material coming out as well, perhaps some stalling and star formation within that disk as well, which I didn't get a chance to really talk much about. But there are indications of star formation as well. And to get into more of a detailed kinematic analysis, just to show what's possible, both with the near infrared data as well as the analysis of the CO detected with ALMA. Here's the case of NGC 5642. And so the near infrared data is shown. Here's the flux of the molecular hydrogen. And we see indications in this case of a spiral structure here. So subtracting an azimuthally symmetric velocity structure, velocity field reads, or sorry, flux. Subtracting that symmetric light, we see residuals here where there's extra components along these orange lines here, which indicate where the dust lines are known to be. So a really key part of understanding what we're seeing, especially in the kinematics of these galaxies, is to understand things on larger scales, which we're able to achieve with HST imaging. So that HST imaging and generating the dust maps, as well as the color maps indicate where outflows are. This white region here, for example, this is outflow. And we see outflow through other indicators as well, but by understanding things on a larger scale, which is possible with imaging with HST, we can then connect those with structures that we see on the small scales that we are able to observe with the near infrared IFUs. And so there's dust structures here in dark. So that's the reddened component in this dust map. And then those are also mapped here. And this is where we can see there's, even in this case, and this is actually quite unusual to see the structure in the molecular hydrogen flux distribution. More commonly is that we see indications of the inflow along those dust structures in the kinematics. And so here's the velocity field of the molecular hydrogen in this galaxy. And you can see it's far from just circular. If it were circular, we'd see just red on one side, blue on the other. You can see there's this big kind of tongue of red structure, red velocities here. The blue is kind of wrapping around here. So there's a lot more going on there than just rotation. It's dominated by rotation. There's a strong rotational component there when we model it. But we also see non-circular motion. So here's just a simple disk model constrained by what we know of how the stars are rotating. And then here's the residuals. So we see blue shifted along this spiral arm here. So it's flowing inward. And then we see velocity structure along the other three arms as well. In this region, which we know is the outflow, it's strongly redshifted. So the molecular hydrogen, the warm molecular hydrogen traced with near infrared is outflowing. We also see this is in the dispersion of the molecular hydrogen where it's highly disturbed in the same region. And in the ALMA, so here's a kind of a zoom into the ALMA map of the cold. So it's the CO gas. It's the same scale as this black box here. And you can see that, again, rotational component is dominant in the cold gas, but even in this cold molecular gas, we see indications of non-circular motions. In particular, there's a component of outflow where you can see in that outflow region here that the gas is disturbed away from that rotational component. So we're seeing a lot of similarity in what we're seeing in the near infrared. That rotational component is consistent with what we see with ALMA, and even with ALMA in that cold gas, we can trace some outflows as well as inflows. And this brings me to the last survey I wanted to highlight, and I'll talk a bit about JWST. The GATOS survey, which is a volume limited Southern survey, selected again on the hard X-rays. And so this is ALMA data. Well, we're waiting for JWST data to come in. We've also have near-infrared imaging that's yielded some interesting results, as well as the near-infrared IFU data, much of which I've been presenting. It's been pulled from other surveys. And we've combined the GATOS sample with the NUGA sample, the NUGA sample being a terrific survey in which they were able to, using a toric approach to analysis, to track the inflows and outflows in these galaxies. The NUGA sample was lower X-ray luminosities, AGN. And so the GATOS sample is very complementary in that combining the two, although the GATOS sample spans quite a range in X-ray luminosities, but combined with the NUGA sample, it's spanning 4.5 dex in AGN luminosity as well, quite a 5 dex in column densities, and quite a range in Eddington ratios as well. And so this allows us to identify how these fundamental properties of the AGN might influence things such as the outflow and inflow, and what that dynamical obscuring structure in the central region might look like. So I'm just going to very briefly go through these next 2 slides because Christina did a great job of presenting our GATOS results. So I'll just highlight some of these, and that, so with the CO and continuum dust emission traced with ALMA, we see that in the dust continuum, there's a bright point source, but there's also an extended disk-like emission. There's also large molecular tori found in CO on scales about 40 parsecs was median for the sample, with masses of 6 × 10⁵. The important point here is that these dusty molecular tori, they connect with the host galaxy through the various dynamical processes, inflow of material, for example, but morphologically they're decoupled, and they're often perpendicular to the ionization cone, suggesting that this is the obscuring structure, that this torus-like structure that we've been looking for, and in that they're perpendicular to the ionization cones where that outflow is occurring. And shown here, you can see that the continuum in color is a CO emission, and then in the lines here, blue, for example, this is NGC 5643, where that outflow is occurring in this region. So the outflow major axis here, or ionization axis, and then the opening angle of that outflow is depicted by the other outer lines. And so you can see how those outflows coincide with the structures that we see in the cold gas. And what came out of this, one of the most interesting things I think that came out of this study is a dependence of the central concentration of the gas on the X-ray luminosity, and this potential for seeing AGN feedback on the circumnuclear scales. So this is, again, a combination of the GATOS sample, but also with the NUGA sample, which allowed it to extend down to the lower AGN luminosities. And the plot on the left is showing the surface density of the CO gas on 50 parsec scales compared to 200 parsecs. And then on the right, this is the torus scales. So what was measured to be the torus size in CO compared again to the 200 parsec scales. And we see that decreases with increasing X-ray luminosity. And so this has been interpreted as we have a structure here where red represents that obscuring structure at lower luminosities. We have a pretty stable situation, whereas as that Eddington ratio goes up, the X-ray luminosities go up, that outflow becomes more prominent and changes the structure. And so it carries, it changes where that material would be located, and we see that AGN wind. This is combined with the second paper that we have from the GATOS survey, in which it's mid-infrared imaging. And so combining where is the cold gas traced with CO, where's the dust emission from the continuum, with asking where the mid-infrared dust emission is. And so what we find in this sample is that there's an extended component, around 50 to 200 parsecs mid-infrared emission in a polar structure along the AGN wind axis. So perpendicular to the torus that's being detected with ALMA. And this is in 6 of the 12 galaxies that this has been detected. And so going back to this picture here, we can see that dusty outflow being carried out. We have, ionized gas in this region, and then we have dust getting thrown up into that region or carried off into that region as well. And then here, I'll just quickly show, since Christina was able to talk about this quite a bit, we see various structures, those galaxies in which we see that polar dust outflow are shown in the kind of vertical oval here, those with an equatorial emission, so consistent with the CO disk. We see kind of a horizontal oval, and simulations would suggest that there's kind of a sweet spot for polar outflows, and that you can't have, if the Eddington ratio is too low, you're not going to propagate that outflow outward. But it's also going to be the case that even if you have a higher Eddington luminosity, then you're going to need to have the material present to produce that dusty polar emission, that outflow to be carrying the dust forward. And so you need to have a column density that will support that as well. And so in those regions where the simulations would suggest we should see our mid-infrared polar outflows, are galaxies where we do see that. So there seems to be some consistency there. And the direction that this is moving now is comparing the warm molecular gas that we see in the near infrared. So these maps here of NDC 4388 with what we see in the CO gas. So that those equivalent on the same color scale are shown in the bottom here. The contours of the flux are shown above. And you can see there's general consistency here, and that the velocity structure has some similarities. The dispersion is quite a bit higher in the warm molecular gas, as you would expect, compared to the CO. And I can show that just in as quick azimuthal average here. You can see elevated dispersion in the warm molecular gas. In this case, we see general consistency with the flux structure, both where the CO gas is emitting and where the warm molecular H2 is emitting. But we do have cases where that is not true. So here's the warm molecular gas velocity structure shown in color here. It's centrally concentrated, and we see hints of these arm structures here. In CO, we see a deficit in the central region. So something has cleared out the CO from the central region, presumably the AGN wind. And then we see much more prominently the CO is in these structures that are hinted at in the H2 up here. So a detailed comparison of the kinematics here is work yet to come that we're very excited to get going. I'll just quickly share this preliminary results here. Doing the same exercise, looking at the central concentration of the cold CO gas and looking at the central concentration of the warm molecular gas traced in H2. I don't yet have the NUGA galaxies to add here, just the one, actually 2 NUGA galaxies to add to this. But perhaps there's also a trend with X-ray luminosity in the warm molecular gas that we're tracing in H2 in near infrared as well. So I think I've pushed my time quite a bit here. So I'm just going to quickly highlight, there's so much we're going to be able to do with JWST, and we have 2 programs approved with the GATO sample that we're really excited to work with. So the list is very long for all that we can do with JWST, but there's more tracing of the inflows and outflows with the mid-infrared detected molecular hydrogen, as well as the ionized lines. There's also a lot that can be done because there's so many rotational H2 lines detected in the near-infrared. We can use those line ratios to directly measure the gas temperatures and the spatial variations potentially along outflows. Is there the temperature gradient along the outflow that we can track with the molecular hydrogen, for example? And then we can also, of course, with abundance of H2 lines, consider excitation models. Extinction models, and then excitation as well with the abundance of low and high excitation lines. There's also, of course, the PAW emission in the mid-infrared. There's just so much we can do. So there's a lot. I think this this picture of a dynamic torus will become much more complete once we have James Webb data available. So I'll just, certainly spelling conclusions wrong, but I'll highlight my conclusions that that new picture of this dynamic obscuring structure in the central region, where we have dust winds carrying material upward. We have molecular gas sitting in a disk here. We have warm molecular gas here. Again, I didn't get to talk about it, but star formation potentially occurring in this region as well. And so this gives us more of a detailed model in which to kind of test our, use our observations to test these kinds of models of what the actual physical processes are in the central region. And then, of course, the next steps, we really need to get down to the smaller scales. We need to be able to test this region here within the central 10 parsecs to be able to really push these models and test them more thoroughly. And then we just need larger sample sizes to be able to do this, which is painful because every galaxy, you have to do this very detailed analysis to really understand what's happening. But without the statistics, it's hard to draw any general conclusions. So I will leave it there. Happy to take questions. Oh, Peter, you're muted.
Oops. Thanks. I didn't sleep all night from a sick pet. But so anyhow, thank you so much, Erin. That was an excellent talk with amazing data and results presented. So questions for Erin.
Erin, I have a question which is a little bit tangential to the main things you were saying, but just put it out there. Do you think that you may have any cases where you would be so bold as to claim that the outflow or the ionization cone or whatever that is really extremely asymmetric, very one-sided, or maybe all of the cases where it kind of looks that way is just, you can explain them away with an awful lot of extinction, and they're really all, if you could just see them properly and observe them the right way, they really would all be basically quite bisymmetric?
So I think, well, I hesitate to say for sure, because the detailed kinematic modeling of the CO data in particular is still ongoing. So I won't jump the gun and give conclusions there of others' work. But from what I've seen, I think working in the near infrared, we can pretty much, we can look to extinction to explain it and feel pretty comfortable with that. I think we'll be able to give a much more complete answer to such a question once we can bring the multi-wavelength analysis together and look at the CO and bring in what we know from the near infrared, where we might have explained it away by saying simply, we only see it on one side because of extinction. But now if we can actually constrain what that extinction actually is, if we can use JWST, for example, to really pin down what is the extinction spatially, can we justify that conclusion that we can't see the other side of this outflow simply because of extinction? Or if we can't, then maybe we'd have to come up with a nice model to explain why it would be not symmetric. I think that there's a lot of material present, right? Once it starts interacting with the host galaxy, these outflows are not necessarily all aligned with the host galaxy all the way out, right? So if this outflow in the central region, it can be pretty much at any random orientation, right, with respect to the host galaxy. So once it starts to propagate outward and interact with things, it can certainly be, I would say, different on one side than the other, because it's not going to be
the galaxy
a
is running into
distribution.
is different on one side than the other. Yeah, that's a good point. But still, I'm thinking that if extinction is certainly an issue in the near infrared, then that would mean if it looks kind of lopsided and asymmetric, that means that you're preferentially seeing the front side, the side that's towards us. Yeah. So isn't that supposed to be a blue shift? Not. the redshift. I'm just thinking of 5643, where it seems like the main thing you
Yeah.
see is this quite strong redshift, not the blue shift, just the
So that,
redshift.
yeah, and I think, and that's the big key to understanding what we're observing. So we can measure the velocity, and we can model it all we want, but the thing is, we have to have that disk orientation correct. We have to understand what's the near side, what's the far side to interpret that. You can simply interpret an outflow as an inflow if you just flip your disk orientation around and have things completely off. And so using the various tools we have available, whether it's HST imaging or O3 maps, to try to figure out where things are with respect to our line of sight. I think, yes, Matt pointing out that once you feel confident in your setting that disk orientation, if you have an outflow that's going the wrong direction, then you might have things completely off. And you can look at the molecular gas, and you can, in that case, you can confuse inflows for outflows because that gas is potentially doing both. But if you're looking at a silicon-6 map, then that gas is not inflowing towards your black hole. It has to be outflowing. And Francisco has shown this, that the silicon-6 line is tracing outflows. O3 is tracing outflows. So when we have those additional components to the picture, it helps us really nail down what we're looking at, what that kinematic component represents. And that can be a really tricky business. But once, if we can bring all the pieces of the puzzle, or at least enough of the pieces of the puzzle to the table, then it starts to make sense. And then I think cases like 5643, where you've got an outflow, in an orientation not necessarily expected, then you can start feeling that you've got a case where it's not symmetric. And
Okay.
I think that we will build up that sample as that
Yeah.
analysis becomes complete. I think we'll find more of those cases.
Cool.
Great. Any other questions? Anybody?
Well, I have several. So
Yeah, I do too, but I'll let other people go first.
but yeah, I wanted to let other people ask, but since this is a little bit related, well, first of all, excellent talk. I really enjoyed it. And just a little related in terms of how your observations connect to the larger scales in galaxies. And I know you did some work on this. I don't know if you've continued some years ago, but I was a little intrigued, with the misaligned H2 disks, and it makes me wonder. I mean, I think it is compelling to see that trend, that at higher luminosities you get more of a misaligned component. But I wonder if there's any connection with inflows, like or alignment with filaments, and I'm wondering if there are any plans to look at the larger picture and try to make connections.
Yes, so I think it's essential that we connect it with the larger scale structures. In a lot of cases, we see non-circular motions in the near-infrared detected molecular hydrogen, for example. And it's just not possible with a small field of view that we have, which is great because it means we also have the spatial resolution we need to really nail down what the kinematics are doing. But it's just too small a field of view to understand in what context these motions are occurring. And so using the HST imaging is very helpful with that. And also ALMA's much larger field of view for those galaxies where that data is available is extremely helpful, because we can trace in the cold gas what that inflow may be, for example, and then connect that with what we see in the near infrared. And then we can identify these are regions of inflow. And then if we also see something else happening, and that coincides spatially with what we see happening with higher ionization lines like silicon-6, then we can feel pretty confident that's an outflow region. And then there are cases where that also is showing outflow activities in the CO cold gas that we measure. So we need all of the bits to understand things, and that larger scale connection with the host galaxy is really important. And I think that our connecting, we're seeing that the structure on 100 parsec scales. In many cases, especially in ALMA data, it seems to be decoupled from what's going on with the host galaxy, but it's not that it's completely isolated. There's still this connection with the inflow of material has to be brought in to support that buildup of material in the center. And so that inflow is that connection that we see. And there's, of course, the outflow could be influencing things if it's significant enough out on larger scales as well. But the inflow has to occur. So that's another significant connection there.
Great. Anne?
Hi, thanks everyone, and thanks Erin for the great talk. I wonder, sort of leading on to what you were just talking about. So in cases, like I'm really intrigued also by this whole misaligned H2, like my first instinct is like, it can't be a misaligned disk, but it's just these non-circular motions and it looks like the PA is offset maybe. I wonder in cases where you have the K-band H2 and also ALMA, do the kinematics match?
Yes, so this is what I'd say is I think when I do the full kinemetry, when I complete the full kinemetry analysis, I think then with the H2, we'll be able to say this is the rotational component and this is an inflow, this is an outflow component. I do think that what we're seeing in that misalignment of the molecular gas compared to the stars on the 100 parsec scales is driven largely by the non-circular motions that we see skewing where the position angle is that we infer from the molecular gas. And that really proves the point that we need the stars to identify what that rotational component ought to be to then isolate what the non-circular motions are. And so, yes, I can say in what analyses I've done, which is just in a handful of galaxies thus far, the CO, the cold gas, aligns, well, I'll put it the other way, the warm gas that we see with H2 matches well with the cold gas kinematics, that rotational component. And so if we can take a case where we're confident in isolating what the rotational component is, and then any other non-circular components, we can separate those. Looking at the rotational component in the warm gas, it matches well with what we're seeing in the cold gas.
Okay, thanks.
Yeah.
Great. Any other questions from anyone? Okay, let's see any hands up. I can ask my questions afterwards if you want to stay on a little bit if you have time, Erin, and
Sure.
anybody else, in a smaller group if they want to hang on for the questions and ideas that I was thinking about afterwards. But maybe we can thank everybody right now. And thank you so much, Erin, for that excellent talk. So let's give Erin a hand again. And I wanted to thank all of the speakers during the seminar series for giving such excellent and inspiring talks. It's really been a pleasure to follow all of your work and then engage in these really inspiring collective discussions. And I also wanted to thank the audience for spending time with us during the summer. It's really been a pleasure listening to you, and I know how much we're on Zoom and how draining it's been. So I thank everybody for joining us in this effort this summer. And Gabby, I don't know if you want to say any words about the.
I think we might have lost Gabby.
Oops, okay, we lost Gabby. Not sure what happened there. But before we end, I did want to say I'm going to send an email out to see if there's interest in continuing the seminar series, maybe on a monthly basis during the academic year. So I'll ask people if they're interested. And some people have indicated interest in broadening it, including instrumentation or future facilities kinds of talks. And I'd also like to see any interest that people might have in actually giving talks at the seminar series if they're interested in continuing it. And in addition, if people are interested in engaging in these brainstorming collaborative sort of discussions that we have had in smaller groups, discussing maybe upcoming proposal opportunities or upcoming JWST data, since a lot of people here are involved in JWST, or CAC or any other facilities. I'll be sending, we can send emails to discuss if you're interested in any such sessions. And then I wanted to say that our students have been engaged in a summer sort of review session. I had mentioned it at a previous talk, and I think Gabby also mentioned how our students have been getting together and doing presentations on reviewing basic AGN physics, how to measure black hole masses, and the topics have been synergistically chosen to complement these talks. And so if you have students that you think would be interested in participating in this sort of review, let us know. And we also are planning a graduate student symposium where the grad students, or undergraduates for that matter, can present their research to a broader audience. And if you're interested in having something like that, in the future with a bigger group across institutions, let us know. And then finally, we had discussed having a Discord server amongst students, sort of like an international AGN alliance or something to build a network. And so, maybe it could be an opportunity to share ideas, talk about, hey, I have this Python code that can do this, skills like how to reduce this kind of data or that kind of data, and just general networking and community building amongst the student population. If you're interested in any of those ideas, it would be really nice to hear from you. So we will send an email just to see if there's interest in any of those things. So with that, Gabby, I had asked before if you wanted to say any last words since this is our last seminar. And then, maybe a smaller group. If Erin, if you have time for my few questions, that would be great.
Yeah, sorry, I had a power outage and now I'm using my hotspot to to log on. No, I think you covered everything, Shovita. I just wanted to thank everyone again for a very, very invigorating seminar series. I was very inspired by all the talks, and I appreciate everyone's willingness to take some time during the summer to share their results, their projects, and everyone in the audience too. So thank you, everyone.